Video we're going to look at more on play and contrast, and we're actually going to get our hands dirty this time and get into R and see how we set these things up. And I think that's really where you see the true advantage to conducting these things. So guys, anyway, in the last two videos I hope you have a better understanding of play and contrast and how they are different from just a straightforward post hoc. I think in terms of experimental control, it allows you to focus on more specific research questions, and kind of improve motivations of studies. So, and I think the supplemental instruction data set that we'll continue to use is actually pretty good for doing that. So we're going to focus this video on how to handle contrast in R. And when we run post hoc, which I'll do a little bit later on this data set, we really don't have to tell R anything more than which post hoc we want to run. Do we want to run just multiple comparisons where we don't control for the inflated type 1 error rate? That would be wrong. That would be bad. Or do we want to run Bonferroni, Holm, Tukey, Chaffee? Which do we want to run? But other than that, R does everything for us. It's harder in R to set up contrast, but it's something that's clearly doable. Now, I think it's no, I don't think, I know, because I know what we're going to do. It's kind of a good time here to revisit dummy variables. And for those of you that took 5500 under me, you probably remember dummy variables. And again, here we are again, ANOVA kind of thought of in the context of regression. But anyway, those of you that took 5500 from me, you know it near the end of the class when we were in matrix operations to find, various things, variance, covariance matrices, and our beta. Our coefficient estimates, we used matrices and operations, and we talked about these dummy variables. So at the end of the day, what a dummy variable allows us to do, it allows us to address issues where we have categorical predictors. So let's just examine one of them, okay? So we have a categorical predictor with more than 2 levels. Now, by definition, even if we have 2 levels, for example, gender, we still, in a sense, I remember years ago, Melissa Gibson now, took a statistics class from me. I think it was Melissa. I may be picking on you, and you didn't even do that. But it's funny. I remember 2 things about her. Well, I remember more than 2 things, but I remember, number 1, how neatly she wrote. But number 2, I remember she always told me, she said, "Dr. Darbo, you always make male number 1 and female 0. Why do you do that?" So Melissa, correct me. Maybe you didn't even say that. Maybe I'm just making this stuff up. But guys, anyway, we still use dummy variables, but the whole idea of setting up dummy variables and seeing how they operate in multiple regression doesn't really come through unless we have more than 2 levels. So let's say, for example, that I have a categorical variable with 4 levels. And we might just say that these are different school districts, A, B, C, and D. Now, for obvious reasons, we can't just insert this variable into our model because the interpretations are the integrity of the interpretations are literally destroyed. When we have a quantitative predictor, for example, if we want to predict GPA in college based on having an intercept model, and maybe we want to take high school GPA, and maybe we want to add ACT. In this situation right here, if we want to tap into the interpretation of the beta 2, we would say that controlling for high school GPA, the predicted first-year college GPA, and let's just say that the this coefficient was, I don't know, 0.12, whatever. We would say that for each additional increase in the ACT, the predicted GPA in college would increase by 0.12. If this was negative, it would decrease by 0.12. But in other words, my point is increasing the value when we have a quantitative predictor by 1 unit leads into the interpretation of that particular coefficient. Now, what does it mean to increase this 1 unit? Well, it doesn't mean anything because these are arbitrary assignments. These are school district A, B, C, D. I don't think there's anything holy about this school district where it needs to be the first one. It could have been put over here. There's no natural assignment of ordering, and so we can't look at the traditional interpretation of the regression coefficients. So what do we do? Well, the first step, I'm just curious, do you guys remember this? Okay, that's one of the disadvantages to not meeting in the classroom is, as a teacher, professor, instructor, whatever hat we wear, when we watch our students and we ask a question they don't know, typically nobody will make eye contact with you. So it's something that is easily hidden in this format. But anyway, the first step we do is we choose a comparison group. And I don't know, just for the sake of this illustration, let's just say that my comparison group is A. The next thing we do create K minus 1 new variables. Now, the language that I use in 5500, and I'm going to be consistent with that here, is I would call this, I think we call it dumb var 1, but I'm going to call it dumb 1, dummy 2, and dummy 3. The purpose of dummy 1, dummy 2, dummy 3 is to make comparisons to our chosen group. Dummy 1, we're going to allow to compare group B to group A. Dummy 2 will compare group C to group A. And dummy 3 will compare group D to group A. Now, what we do that's worthwhile, at least in my opinion, the reason I wanted to revisit that is how do we set up our dummy variables? Well, what we do is for each observation A, B, C, D, we make our coding in these new variables set the intent of the variable. So dummy 1 compares group A, or I should say, when we see, let's work from left to right here. When we see A, then we want zeros everywhere. Guys, hold on just a second. I've got to get my charger. My computer's getting ready to go dead. All right, guys. Sorry about that. But showed that I had like 2% charge left, and I didn't want that to happen for obvious reasons. But anyway, where we see B, remembering that dummy 1 was a comparison of B to A, we would have the following. And C is a comparison. And we put a 1 in for D3 because D3 is a comparison of variable D to A. So we use zeros and ones to set up these dummy variables. And I'm sure most of you remember that, but didn't want to take the chance. All right. Now, in regression, these dummy variables serve as weights. And the reason that I thought that it was important for us to kind of to revisit these weights is to set up the rules for playing comparisons. And I got to give my old buddy Andy Field credit here. I looked at different resources, and I like the way that he presented this best. And this is I know we've had rules before. We had a big rule, and then we had 3 rules, and then we had four rules. We had all sorts of rules. These are really, I mean, once we get down to the nitty gritty, the things that we need to do, according to Andy Field, who's 10 times cooler than me. First of all, he says, be sensible. Compare 2 chunks of variation. And, if a group is simplified or singled out, then it shouldn't be used again, okay? We've talked about that just a little bit. The second thing we do is we code one group positive values and the other negative values. The third thing we need to do is the sum of the weights. Must always be 0 to have orthogonal contrast. Second thing, we assign groups not used in a contrast a value of 0. Now guys, if you think back to the contrast that we set up, the first contrast we set up did a straightforward comparison of the experimental control, and the second contrast jumps into the experimental and compared the 5 hours versus the 10 hours. Notice that the control group wasn't included in the second contrast, so in that situation it would get a contrast value of 0. And finally, for a given contrast, all right, for a, got them running out of paper down here. Let's see if we can get this worked out. All right, for a given contrast, the weights assigned to the group or groups in, let's say, in one chunk. Must be equal to the number of groups in the other chunk. Now that's probably the most complicated. It's really not even that complicated, but it's probably the one that isn't as clear when you first see the rule. So guys, let's go back and see where we are and how we'd weight these things, because it's going to be really important when we get into R that we can share the weighting when we set up our contrast in R. So guys, remember we have three groups. All right, first group is the control. Second group is what I call the experimental stage 1, 5 hours. And the third is the experimental 2 of 10 hours. Contrast number 1. Is the experimental 1, experimental 2 versus the control. In contrast number 2, examines the difference in means, if you will, with some correction, for the supplemental instruction programs 5 hours and 10 hours. Now, for contrast number 1, following the rules that we set up before, rule number 2 states that we give one side positive and one side negative. So experimental, control. And guys, it doesn't matter, but I'm going to set the first one as a positive and the second one as a negative. Okay? Rule number 5 states that the weights are equal to the number of groups in the other group. Now over here we have this, and I should have written this as experimental 2. So that's telling me that when I focus on the control, the number of groups in the other chunk of variation is equal to 2, so I have to have a magnitude of 2 for the control. And when I look at the experimental chunk of variation, the number of groups in the control are actually 1. So since I've given this side negative 1, this is actually going to come out to be a negative 2, putting all this stuff together. And I have 1s on this side. I'm going to have a 1 for the 5-hour chunk of variation, and I have a 1 for the 10-hour chunk of variation. Rule number 3 says that the sum of the weights must be 0. I know this goes without saying, but 1 plus 1 minus 2 is equal to 0. All right. Our second contrast. If you can see it. All right. Now, here we've got used stuff and unused stuff. So we have, remember the control was used in the previous contrast. There was no way to break that down further, so that's going to be unused in the second contrast. So I forget which rule it was, but that says any contrast that's unused will get a 0. The used chunks of variation turn out to be the 5 and the 10. And again, it's kind of repeating. One has to be positive. One has to be negative. The numbers that we assign We assign the number to the group 5 based on the number of levels over in the group 10. Well, that's 1. And we examine the 10. We give it a number based on the number of groups over in this, so it's 1. We're going to give this a positive, and we're going to give this a negative. Now, clearly, 1 minus 1 is equal to 0. So, guys, we may want to look at an organization. And so here's what... and this is a really important presentation of our results here because it allows us to get into independence and orthogonality. But anyway, guys, at the central focus of this would be the 3 levels of our independent variable, the control, experimental 1, experimental 2. So we have contrast 1 and contrast 2. So if we examine contrast 1, control got a weight of negative 2. And each of these got a weight of 1. Guys, this sum has to be 0. Contrast number 2, since control wasn't used, we give it a 0. And I forget which one got positive. I think it was the 5. And the sum is 0. But guys, what we need here is we need contrast 1 times contrast 2 to also be calculated because the sum of the products tells us an important characteristic of our overall contrast model, if you will. So multiplying 2 times, or negative 2 times 0 and 1 and negative 1, when we examine this sum, which is clearly equal to 0, this tells us that we have independence and an orthogonal, well, I should say not and, but thus, an orthogonal contrast situation. Guys, it all kind of, at the end of the day, and I don't want to beat a dead horse and just go crazy on this, how regression and ANOVA are so closely related, but it all kind of goes back to, again, to regression. If we're going to run a regression model, what would we do? Well, we'd probably run the linear model. And then we'd probably look at the ANOVA output, where we would have a model term. Well, actually, for the ANOVA for this, we'd have a regression. So what source of, or what percentage of variation can be attributed to the model? Y regressed on our set of predictors. And, the other part is the error. And, of course, we have sum of squares and degrees of freedom. You guys have seen these ad nauseum. But something else we do is we would want to come in and get our coefficient information. And what this typically looks like, it's been a while, and that's why I'm going to show you this, is you typically have your estimates, how many there may be. And the first thing you have is your estimate. And the next thing we have is usually the t-value. And then we come up with a p-value, and sometimes we get into the 95% confidence interval. Well, you got to ask yourself, if you're really, really, really thinking, how can we do this? Because at the end of the day, these things are just multiple t-tests. And if multiple t-tests aren't acceptable in ANOVA, and this whole ANOVA regression connection is, and I promise you it is, how do we get away with that? Well, guys, the way we can get away with this is a certain assumption. And we assume that our variables aren't highly correlated. Now, I don't know who you're going to take 6,500 from, but if you take 6,500 as it's currently presented, this gets us into a situation called multicollinearity. Well, guys, as long as our these variables aren't highly correlated, we end up getting independence, because that's, in the correlation sense, that's exactly what independence means, is that our predictor variables aren't correlated, they're not related. And thus, if we aren't highly correlated, we have independence, and by conducting these pairwise tests, we don't inflate our type 1 error rate. That's really the connection back to the sum of the products turning out to be 0. That gives us an indication that the assumption of independence hasn't been violated. So really, at the end of the day, it's actually that simple. So that last column that I showed you is extremely important. All right, gang, let's get out of here and go do some hands-on stuff. All right. So things that we're going to need in R, we're going to need a couple of new things. First of all, there's a contrast command that we'll end up using. We'll use an old buddy, the AOV command, and we'll also use a new one called summary.lm that I'll show you. I think we do. Yeah, I don't know. We'll just have to go with the flow on that one. So let's see how we carry this out. Now, after running the model like I've done here, the easiest thing to do is to just conduct straightforward post hocs. And we should know now that we've got some some ways to do that. First of all, we can just do a pairwise t-test of our y over our group with no p adjustment. And in that situation, actually, okay, I didn't realize that. When you don't put in the p-adjust, the default is to run a home p-adjustment. Okay, so that's kind of cool. Another thing we could do is to run, no, I misspelled, okay. Is to run the Bonferroni p-value adjustment method. And you can see that home is a little more aggressive when it detects a difference. Notice there's no difference in the p-value, but when it doesn't detect a difference, there's actually a difference. What Bonferroni actually does is it calculates a straightforward p-value from a t-test, and then it multiplies it by the number of comparisons that it's making. The home actually goes head first, and it actually looks at a much more aggressive approach. My favorite, and if I'm going to depend on anybody, it's going to be Tukey, and I tend to like the Tukey comparison. You don't get from just the Tukey comparison that we get on R, you don't get the p-values, but no, actually you do. You get the p-adjust. I'm sorry, I didn't realize that. And it actually usually turns out to be a little more aggressive. Let's see. So the detection, yeah, 0.029 versus 0.034. So your p-value is actually a little smaller. But what I like about using Tukey is it gives us the lower and upper bounds of the confidence interval. Keeping in mind that we've adjusted the p-value to control for the inflated type 1 error rate. Now, I'm going to show you first of all what I don't want you to do. It turns out that R has some built-in contrast. And the first thing we've got to do when we run any kind of contrast is we have to tell R that we want contrast run for a particular for our dependent variable. And then we want to come in with the contrast instructions. Probably of the standard contrast, I think a lot of people would agree that the Helmert is the one that I see reported the most. And what R wants you to do there is put K, which is the number of groups, so back to the control, supplemental instruction 5 and supplemental instruction 10. We would have 3 groups. And that's what Helmert would do. Now, what Helmert does is it takes each category except the last one, and it compares to all the subsequent groups. So it wouldn't compare control and experimental. It would focus on the last one, which in this case would be the 10 hours, and it would compare it to the other ones, and you can see by the contrast that that's exactly what's happened. There's another one. There's a CONTR dot treatment. I really don't like that one at all. So, but guys, what I want to get into is I want to show you how to create your own contrast. In other words, I want to model on R what we have done with this control supplemental instruction 5 and 10. So the first thing I would want to do is establish my contrast. So I'm just going to call this first one contrast 1. And I'm going to use the C function. Now, what I have to do is I have to go back into contrast 1, and remember I've got to put these in terms of the way that they're presented in the data set. Now, I've got this kind of arranged according to control EXP1, EXP2. But if these things were mixed in, let's say I had to score 2 arranged from lowest to high, the first group that you see, it may not all be clustered together, but the first one you see is going to be what you need to put in first. Well, in this case, it's control. And for the first contrast, we gave that a -2. For experimental 1, we gave it a 1. And for experimental 2, we gave it a 1. Again, noticing that the sum is 0. For contrast 2, again, starting from the top, remember we didn't include the control group in there, so we gave it a 0. And I think we gave the next one a +1, and we gave the next one a -1. Now, the next thing we're going to do is we're going to create a contrast grouping. And what we do here is we put the name of the data set, $, the dependent variable. And we use what's called the cbind. And I want to bond contrast 1 and contrast 2. This is kind of like a kind of a mashing. It kind of creates, in a sense, a linear composite of the contrast. It kind of mashes them together, and we end up making our comparisons this way. All right, what did I do? Oh, I know what it is. Should be contrast. Okay. Guys, I promise you I can contrast. I can spell, I just can't see. All right, before I hit enter, let me check this. This is getting old. So contrast data group. So this part right here is the name of the data set we're using, and we're kind of creating a new data set by focusing on restructuring the group term according to these contrasts. So this should work. Okay, cool. Now, just to see the fruits of our labor. You can see that the contrasts that we have here look exactly like the summary table that I gave you before. All right, so that's kind of cool. Now, the next thing we do is we actually create a new model. So I'm going to call this new model, I usually just call it model 1, model 2, model, and so on. But I want to give it a name for something that indicates the process that we're learning. And I want to run AOV. And I want to run the score 2, as you would imagine, over the group. And because I've kind of created this new data set right back here, I don't think it's going to interfere with what I want to do. But I'm getting tired of the red pop-ups, so I'm just going to tell it that the data we want to use is the one that we opened up, way back here as data. I just don't want any more red stuff. Okay. Now, guys, if I go this, and this is not what I want to do, but I just want to show you that if I do summary model planned, I'm not going to get anything different than I got when I originally ran my ANOVA back in a previous video. That's not what I want. What I want to run here is I want to run this new command called summary.lm for this model planned. Now when I do that, I get exactly what I want. I get my planned contrast. And what it does across the group term, which is my independent variable. Let me just go through this, each one of these. Guys, this is irrelevant. We don't care about the intercept. It doesn't have an interpretation that I'm interested in. Group contrast 1, this is where we compare the experimental versus the control. So I could go to my administrators and say, well, there is a difference. There's a difference in these quiz scores, I think is the way I set it up, is statistically significant across those who used some level of supplemental instruction versus those in the control group who didn't use supplemental instruction. Guys, contrast 2, in terms of going to the university and selling them that 10 hours is better than 5 hours, as we defined contrast 2 to be in an earlier video, we can see that the difference is not statistically significant. So what that appears to be is, statistically speaking, it appears that there is support from this fictional example that supplemental instruction does work, but the difference in 5 hours in 10 hours is not statistically significant. so the university can save itself money and just implement the 5 hours instead of the 10 hours. So the way you write this up is pretty much the way that you do in other situations. Report the t-value and the p-value and stuff. So, guys, I'm losing my voice. It's getting scratchy. So, guys, I'm going to end here. The next thing I'm going to look at will be, or at least the next video, I want to give you an idea what's up with this bootstrapping method, and then we'll go on into Manova design. So, guys, that's all I got. Take care.